So at the beginning of this chapter on sequences and series, I mentioned that the sequences are really just functions that we only evaluate at the natural numbers. And series are like improper integrals in the sense that they're an infinite sum. You're going out forever. And I even drew a picture, which I'm about to draw again, to try and convince you that there was a connection. And what we want to do is make that connection a little more formal now. And that's what the integral test does. So you can read there, if you have some function, and I've just drawn an arbitrary curve here, but I made it satisfy those three conditions. This function is positive. It's above the x-axis. It's continuous. There's no breaks, jumps, or anything. And it's decreasing, strictly decreasing. So there's no wavy up and down business going on there. And I'm going to draw rectangles to represent the terms of the series. So that's why I've labeled this both the x and the n axis. And this is both the f of x and a sub n. So you've got the function. And so what the test says is if you have a series where the terms are the same as the function evaluated at the natural numbers, and the function has those properties, then the integral will tell you whether the series converges or diverges. That's what we have in the final statement there, that both the series and the integral converge or diverge. So if the integral converges, the series converges. If the integral diverges, the series diverges. This is nice because we know how to integrate, right? We can, if there's an antiderivative, we can take that improper integral and we can see what it does. And from knowing that the integral converges or diverges, we can then conclude something about the series. So this is going to open up a whole class of things that we can do. If the corresponding function is something we know how to integrate, and it's got that positive decreasing continuous, then we're good to go. Okay, so what I'd like to do is argue one way or the other. So let's assume the integral's divergent. So what I want to not really prove, but just convince you with a picture, is that if the integral from n to infinity of f of x diverges, then the series must as well. So in this picture, I'm going to assume that the integral from n to infinity of f of x dx diverges. And actually, it must diverge in a very specific way because the function's positive, right? So as I go out farther and farther in that improper integral, if it's diverging, it must diverge to infinity, right? Because as I bring in more and more, I can really think of it as area because f is positive. So as I move my stopping point farther and farther out in my integration, I'm just getting a larger and larger and larger and larger amount. And since we're going to assume that it's diverging, then it must just go up to infinity. So we actually, since that function is positive, that means that it's not just any old divergence. We know something specific. We know that it's diverging off to infinity. Okay. Now I want to argue that the series is, at any point along the way, is even larger than that. And if this is heading to infinity, the series must as well. So we can think of the terms of our series as rectangles on this graph. I'm going to draw left endpoint rectangles. So, and I'm going to make them all width 1. So the next mark on here is going to be big M plus 1, big M plus 2, big N plus 3, and so on. There's my first rectangle. My second one, and so on, making left endpoint rectangles. But let's think about what the area of those rectangles represent. this rectangle has a height that's determined by the curve at big N. But that's what the terms are. They are the function. So this thing has a height of a sub big N, right? Because that's the same as the function at N. So I have a rectangle whose height is that and whose width is 1. So base times height. That first rectangle just has area that's the same as the first term in the series. Likewise, the height here at big N plus 1, well, that's f at big N, big N plus 1, big N plus 1. And again, the base is 1, so that's a sub big N plus 1. And the next one will be a sub big N plus 2, and so on. We could maybe stick one more on there. And we'll just keep having these rectangles, right? Well, what do we know about the area in relation to the integral? Well, the integral is the area under the curve, but the rectangle is even bigger. So at any point along the way that I stop in my integral, if I stop at a natural number, the current partial sum of the series will be even bigger. So at any point along the way here, the integral from big N, let's say plus some amount, plus k. It's got to be an integer because we're trying to match up with these rectangles. Anywhere you decide to stop along the way, that partial sum of the integral, if you like, is less than the rectangles, which is the sum from big N to big N plus k of our a sub n's. So that's a partial sum, right? So the partial sums are always bigger than that partial integral, if you like. But as we go to infinity, then this thing heads to infinity. So if you keep going to infinity, that's going to diverge as well to infinity. So it's like a size comparison, right? It's the area under the curve is less than the area in the rectangles. And why can we say that for sure? Well, the key part is really this decreasing, right? Because the function is decreasing, every time you make a left-hand point rectangle, its area will capture more than the area under the curve because it's starting at the highest point and the curve only goes down from there. So it's key that the function be decreasing. We also made this argument about it being positive as well, so we could think of it as area. If this starts to go below, then the argument gets a little switched. And so we do want it to be positive, decreasing, and continuous so that we know that the integral diverges in this specific way here. So positive, decreasing, continuous function, you can make this argument. Now, what about the reverse? It seems like this would only work one way. Well, I won't go through the picture again. There's a nice picture in your text, but think about if you did right endpoints instead of left. If you do right endpoints, all your rectangles are going to be below the curve. And you're going to be able to make a similar argument here that the partial sum has to be less than the partial integral. And the integral is converging. So you have we talked about that being monotonic and bounded. Well, the partial sums are monotonic because As you keep adding them up, the partial sums keep getting bigger and bigger and bigger, but they're never bigger than the area under the curve because they're all below the curve. So you use that theorem that we got from the sequences section that a monotonic and bounded sequence converges. And so you can argue that if the integral converges, the series converges. So you've got both. So this is nice. Either way, you're going to be able to make a conclusion. If you have a positive decreasing continuous function and you take the integral, whatever happens, you're good. If that integral converges, then you know the series converges. If that integral diverges, then you know the series diverges. And so we'll look at some examples. One of the ones that we'll use a lot is the one that's based on those reciprocal power functions that we looked at for integrals, because we know something about when those converge and diverge without even integrating them. And then they'll in turn tell us something about the series. So we'll look at those and look at another example. So we'll look at those next.